Hello everyone! In this video we will continue to examine topic 7.2 nuclear reactions, and in particular we will begin to unpack the concept of mass defect and the nuclear binding energy. So in the previous video we were reminded that mass is equivalent to energy, and that mass is a measure of the energy content of the system. And in particular, E is equal to m naught c squared, and c squared is really big. So that begs the question, where is it? What form is this energy in? If you take a really small mass, even a really small one, and multiply by the speed of light squared, you get a tremendous amount of energy. And we haven't sort of seen this energy before, right? It hasn't seemed to sort of be converted into any other type of energy, at least not that we know of. So what form is it in? Where is it most of the time? And the answer is that it's in what's called the nuclear binding energy, okay? Bound up in the nature of the nucleus. And the only way for that energy to change form is to undergo a nuclear reaction. So, to define the nuclear binding energy and unpack a little bit, consider the following situation. Imagine you are going to disassemble a nuclide, a particular nucleus, into its constituent nucleons. If you were to do so, that would require an input of energy because they're very tightly bound, so you sort of have to pull them apart. In practice, you would send a high-energy photon, shown here, right, at your bound system of 2 protons and 2 neutrons, and then in the end, you would have sort of these protons and neutrons just hanging out. Actually, in practice, these guys would be moving pretty fast, so you'd have to be careful about that and sort of take that into account. But let's say for a second you had exactly the right amount of energy simply to separate them and no more. Well, consider the energy and consider the masses. How does the mass of these things, right, those independent nucleons, compare to the mass of this thing, that bound nuclide? Well, we know that mass and energy are equivalent, so we need to be careful about this. We sent a pretty significant amount of energy at the nuclide. And in the end, we simply have these protons and neutrons sitting by themselves. What this tells us is that if energy is to be conserved, if the total amount of energy over here is the same as the total amount of energy over here, then the mass of these protons and neutrons on the right has to be bigger than the mass of the bound system, that helium nucleus, on the left, because there was an input of energy, and the total amount of energy on the left has to be equal to the total amount of energy on the right. This is an incredibly important result and not at all intuitive. Separated nucleons, these nucleons, literally weigh more, have a larger mass than the bound system that they came from, right? If you stick them together, they will weigh less. That's summarized here. The difference in mass between those constituent nucleons and that original nuclide is known as the mass defect. And so the mass defect here, delta M, is defined as the difference in mass between a given nuclide and its constituent nucleons. That can be summarized in the following equation, although really it's just this restated, but delta M is equal to the number of protons, the atomic number, times the mass of the proton, plus the number of neutrons, times the mass of the neutron, minus the mass of the nucleus. So it's the difference between this thing, which are all the protons and neutrons, and the mass of that bound nuclide. That difference in mass is known as the mass defect. Okay? Notice it's not that somehow this energy has been converted into mass. It's that this total amount of energy or mass is the same as this total amount of energy or mass. As it turns out, the inertial properties of this whole system are the same as the inertial properties of the constituent nucleons, although that can be tricky to show. A related concept, the mass defect, is the answer to our original question. So the difference in mass between this bound system and the constituent nuclides corresponds to a certain amount of energy. You simply take delta M and multiply by c squared, and that amount of energy is the binding energy. The full definition is that it is the energy required to separate a nuclide into its constituent nucleons. That is, it's exactly the amount of energy we had to input, and that amount of energy makes up the difference in the mass between the nuclide and these nucleons here. It's the energy equivalent of the mass defect.